So it's my pleasure to invite the first keynote of the day, Professor Omar Ghattas. I met Omar at the Oden Institute in the University of Texas at Austin, courtesy of Karen, Professor Wilcox. We're trying to put things together. And then that was a few years ago. And then when I sent the invitation to Omar, he sent an immediate answer saying, oh, I heard so much things about multi-core world is one of these invitations that you cannot say no to, which I'm flattered and I thank you. So please welcome Professor Ghattas.
All right, thank you very much, Nick. Thank you for the invitation and for bringing together this great community and your hospitality and the great food. And, weather most of the time, too. So I know you had to work on that one. All right, let's see. I'm going to extend the display. And
stuff like that.
That's somewhere. Granted, could be Patagonia. All right. Did I do something wrong?
No, be patient.
Okay.
I don't know how random it is. So, on sanitation.
Thanks, Tommy.
So it's in the bulk, the Horicus.
I extended the display. I should have mirrored the display? Yeah. All right.
Okay.
Top corner, system settings. Oh, there. That's quick one there. And stop extending. And just this one, I think. Entire screen. Okay, great. Thank you. Start mirroring. Yeah. All right. Okay, so I'm going to plug this in.
If you click on, there'll be.
I'm going to plug the power in so it doesn't time out. And I think, is there?
Yep, did the power. Give it to me.
Okay, answer. Got it. That's not. Thank you very much. Okay, so what if I told you we want to solve forward problems that have 10 to the 14th degrees of freedom? And actually, we don't want to solve the forward problem just once. We actually want to solve an inverse problem in which the forward problem has to be solved 10 to the 5th times. And we want to do everything under uncertainty because we have in mind natural hazard problems where the need to quantify uncertainty is critical. And what if I told, this last one, what if I told you that we want to do all of that in real time, in a second or so? Exactly, we want to do it exactly, no approximations, because these problems don't lend themselves to approximations. So you probably say, Omar, you're crazy, right? I mean, you'd probably say that anyway, without that list of desired things we want to do. All right, but that's exactly what we're going to do. And there's no free lunch. We're not violating the no free lunch theorem. What we're doing is exploiting a specific property of these systems that we're after, which is their time invariance. These are autonomous systems. They have invariance with respect to shifts in time. We can exploit that. And we can also design algorithms that map well onto multi-GPU systems and take advantage of these big new systems that are coming online. And we exploit a offline-online decomposition. We do some work offline, but again, which is not huge. It amounts to solving the forward problem order 100 times. Depends on how many sensors we have. And then the online component is mostly, and that's the only time we touch the PDEs offline. So this is modeled by partial differential equations. And that's the expensive part. We touch that only in the offline portion. And then the online portion, it's rich in really FFTs and dense linear algebra. And this decomposition lets us do the online portion in fractions of a second. All right, so the target application that I'll talk about today is Tsunami, early warning of tsunami. So there's seafloor motion due to an earthquake. That creates an uplift in the water column, which creates gravity waves, which then propagate as tsunami and can cause massive devastation. So that's the target application. I'll talk a little bit about the motivation and what's behind some of the physics, but it's more broadly applicable. Okay, this is joint work with Stefan Henneking, who is a research scientist, former PhD student at the Odin Institute, and now has stuck around as a research scientist. Shriram Venkat, who's a current PhD student, Melinda, Fernando, postdoc, and Elise Gabriel is a geophysicist at the Scripps Institute, UCSD. We're collaborating with her. We have a new collaboration with the MFEM folks at Lawrence Livermore National Laboratory. MFEM is a library for modular finite elements that we build everything on top of. We build the offline parts on top of. I'm not yet ready to show results, but we've been running on LCAP. Actually, they've been running on LCAP. We can't touch LCAP. And so we're doing some large scalings, but we're not quite ready. There's still some optimizations. So we're not quite ready to show numbers there yet. Okay, so let's talk a little bit about tsunamis. And so I'm going to show you this video here. I'm going to have to escape. And there we go. Okay, so what you're going to see is this is an oceanic plate, for example, the Pacific plate, and it's subducting underneath a continental plate. So these plates, tectonic plate theory, the plates move around on the Earth's surface. They're driven by convection in the interior, heat rising up, flowing along the surface. The rock flows along the surface, it cools, and it descends. And you get a big convection cell. So plates, in some parts of the planet, plates are being driven towards each other. In other parts, they're diverging, they're moving apart, and that's where you get volcanoes, and that's where you get the creation of new crusts as magma comes up. Other parts, the plates are sliding along each other. But in subduction zones, you have typically a continental plate is the overriding plate, and the oceanic plate, which is thinner and denser, tends to subduct underneath. Now, watch what happens as this evolves. Notice that the plates are locked. So in some portions of the world, the plates are locked due to friction. The continental plate, as this oceanic plate is driven down below, the continental plate experiences uplift, okay? And then on the continental side, on the ocean side, it subsides. See how this is being dragged down? This part is being dragged down here. This is being lifted up. All right, and these plates move a few centimeters per year. So it's this, this is measurable. All right, and it continues, The friction holds it in place. Years go by, 10 years, 100 years, 200 years, and strain accumulates on the fault. And at some point, it's too much. The friction can't hold it. What happens? It's like a spring that's wound up. It suddenly releases massive, hundreds of thousands of atomic bomb equivalents of energy. And the rebounding of the continental plate lifts up a column of water. That column of water creates a gravity wave. And that gravity wave then propagates and eventually inundates the shore, in some sense, it crosses the Pacific on the left. On the right, it heads toward the continent, which might be 20 minutes away, which might have only a 20-minute warning. So what we want to do is take advantage of plans to instrument the seafloor with pressure sensors. And these pressure sensors will measure acoustic waves that are created when you have a sudden uplift. Sudden uplift, acoustic waves bounce around, pressure sensors measure it. We want to take these pressure sensors, solve an inverse problem, and ask, what would the seafloor uplift be in order that we measure what we measure, okay? The forward problem is acoustic wave propagation in the ocean. Acoustic waves at typical 1 hertz frequencies that, we're going up to 1 hertz that we care about, will have wavelengths about 1,500 meters. So we need grid spacing about 150 meters. And our target subduction zones are about 1,000 kilometers long. And that's why we get these massive scale problems. Okay, so that's the inverse problem. infer the seafloor motion, do it in the Bayesian framework, which accounts for uncertainty, and then forward propagate the gravity wave towards shore and make a prediction where inundation will occur and what the heights will be and what the uncertainty is in a fraction of a second or in seconds before the 20 minutes it takes the wave to hit shore. Now, some places will take longer than 20 minutes, an hour, let's say, but this is the basic idea. All right, there's two. So this is the target region. This is the Cascadia rupture zone. And what's happening here, so it's actually not the Pacific plate. The Pacific plate is out here. Cascadia, this subduction zone here, consists of these three oceanic plates, Explorer, Juan de Fuca, and Gorda, that are being driven eastward. They're subducting along this boundary here underneath the North American plate. And there is a region where they're stuck, and that's this region over here. I'll show it in the next slide. There's high probability of rupture within the next 50 years. There hasn't been an earthquake on this fault since the year 1700. Of course, the towns along the coast are at high risk, but even the tsunami waves can propagate through the Juan de Fuca Strait here, and they can cause a lot of damage in Victoria. They can even come down Puget Sound and hit Seattle, even down to Tacoma. Simulations seem to show that Vancouver is shielded. It's hard for them to get up here, but those are simulations. So the next slide will show you the current locked part. So this is the locked part of the fault. So the two plates are locked here. There's friction holding them in place, and the time bomb is ticking. So we know that this subduction zone has produced large earthquakes in the past. And in fact, this wasn't actually known until speculated in the 1980s and sort of confirmed with various evidence in the 1990s. One of the pieces of evidence that led to that conclusion is this. So what is this? This is a ghost forest off the coast of Oregon, which was actually revealed and been covered with sediment, but there had been a large Pacific storm that had scoured sediment and then in low tide revealed these various tree stumps. So what's going on here? And what they pieced together was that there must have been a large tsunami that had led to, remember, when you get that slip, on the land side, you get subsidence. When the spring releases all that energy, subsidence. So these were inundated with seawater that killed the trees. And then they were covered with sand that was deposited by the tsunami, and that sort of preserved them. So they could go in and they could compare these tree stumps with neighboring trees that were still living. They could count the difference in tree rings, work backwards, and say, okay, sometime between 1699 and 1700, there must have been this massive event. And then they went and checked with Japanese colleagues, and they said, you guys have very good written records that go back 1,000 years. Do you see something in 1700? And they say, oh, yeah, there was this freak orphan tsunami, January 26, I think, 29 maybe. Anyway, January of 1700 that reached 3 meters or something, 5 meters, and we had no explanation. We never saw an earthquake, never heard an earthquake. And then they start to go and piece together, you can drill cores and you can see sediment layers that are consistent with silt. You can also find fossilized marine creatures that you can carbon date. You can find them kilometers on shore. So the tsunami must have deposited on shore. And they piece all this together. And by the 1990s, the picture that emerged was that there was a magnitude 9 earthquake, estimated magnitude 9 earthquake in the year 1700. And then you play this detective game and you can go back and you can see the recurrence intervals. And in fact, they've reconstructed 42 earthquakes over the last 10,000 years. That's a recurrence interval about every 250 years. This was the last one. Recurrence. Does anyone have real estate in Seattle or Portland? Okay. All right. So Okay. Oh, great. You'll be in good shape. Yeah. But we'll talk about New Zealand at the end, actually, this time. Because there is a subduction zone off the coast of the North Island. All right. So, seismologists give a 37% probability of a magnitude 8.2 plus event within 15 years, and then a full rupture of the entire Cascadia zone, 1,000 kilometers, is given 10 to 15% probability. So that's a magnitude 9 event. Of course, it's going to cause massive, the seismic waves themselves will be deadly. But what we're interested here is the tsunami waves. Can we infer exactly what this uplift is in real time, make predictions? And this is what we need to be able to do it. So this is a proposal for instrumenting the subduction zone, the entire subduction zone, from Northern California with fiber. So this is fiber that runs through this zone with pressure sensors located here. Now, funny, it sort of ends right at the Canadian borders. Don't know why, but hopefully they'll get, they'll work together and extend this up because there is, considerable. I mean, there's data to be collected here, even if you just cared about the effect on the U.S. But there's a big hazard on Vancouver Island. So the idea is these are the pressure sensors. Solve the inverse problem. The data will be sent back to land. Solve it quickly, and then make predictions. And then that helps not only people to evacuate, but also it helps early responders know where. All right, the model says this is where 20 meters. You can get it. Actually, the magnitude 9 event is thought to have produced 30 meter high tsunamis. So you give early responders time to respond, to plan and say, all right, these regions are devastated, these are not. And this is what a typical pressure sensor will record. So this is about 15 minutes here, these between tick marks. So this is the main, this happens to be a Japan earthquake. This is the main event, lasts about 10 minutes, and then there's some aftershocks a few hours later. Okay, so you might get something like this. But what we're trying to use is this portion right here, the early transients to solve the inverse problem. Okay, we can't wait. There are some buoys out there that measure wave height in the open ocean. We can't wait until the tsunami has propagated to these, there's a handful of them. That's not enough, these dart buoys. That's not going to give you early warning, at least not the rich sort of full description of the spatiotemporal movement of the seafloor that we can get using high fidelity models. The challenge, of course, is to do this in real time. All right, and this is the last piece, which is the forward prediction. All right, and so what you're going to see is now this is using a shallow water code, and maybe I'll talk a little bit about the distinction between that and what we're doing in a little while. So this is an earthquake now, which lifts up a column of water. This is actually not terribly realistic in the sense that the entire seafloor has been lifted up at once. In practice, what will happen is the rupture will start somewhere. It nucleates somewhere. The fault starts to rupture. The waves propagate, and then they do all kinds of crazy things. But even with this sort of uniform uplift, you see the waves inundate. Now, there's a timer down at the bottom. It says 22 minutes there. You can see sort of the waves hit shore about 15, 20 minutes, depending where you are. They propagate down the Juan de Fuca Strait there into the Salish Sea. Victoria is right here. This is Victoria. Vancouver is up there. Of course, there's Seattle and Tacoma is down at the bottom. And you can see, even as it comes down Puget Sound, there's still, 3, 4, 5 meters coming down towards Seattle and then all the way down to Tacoma. Okay, so let's talk about how we actually do this in real time. Okay, so I've said all this already. The goal is to solve the inverse problem from near field pressure data, invert for the spatial temporal seafloor motion. So it's a two-dimensional field in space times time. That's what gives us the very high dimensional inverse problem. We want to pose this as a Bayesian inverse problem. And as I said, we have 10 to the 10th parameter degrees of freedom. That's a spatiotemporal field of the seafloor. And then 10 to the 14th, that's just to resolve the propagating acoustic waves in the three-dimensional ocean. We want to do this in PDEs and in real time. And the difficulty we have is that the forward partial differential equations, acoustic wave propagation, they're what's known as hyperbolic, which means they carry information with them. They don't admit a low-dimensional representation in the traditional ways of low rank or projection type reduced order models. They don't lend themselves to surrogates. This is theoretically proven. This is not just experimental results. And so the approach, as I said in the beginning, was we exploit the linear time invariant structure of the problem. We do some work offline, which is not bad, and then online we solve problems rapidly on multi-GPU systems. So we have to have access in real time to multi-GPU systems. But given the trillions of dollars that such an event, magnitude 9 event in the Pacific Northwest of damage that will be caused, presumably we can afford a cluster of 100 GPUs, let's say, that's ready to go at any time. All right, the forward model. So the acoustic wave equation in the open ocean coupled to the gravity waves of the surface, and what we're inverting for is the seafloor motion. So actually dB dt, B would be the displacement of the sea bottom, dB dt is the velocity. So we're inverting for the seafloor velocity. We have to truncate the domains. We've got some absorbing boundaries on the sides, and of course we're doing this in 3D. Some equations. This is just the acoustic wave equation written in what's called mixed form. So U is the velocity, the acoustic wave velocity. P is the pressure. Rho and K are density and bulk modulus. Then coupled to this acoustic wave equation on the top surface, there's the gravity wave. And the gravity wave, the height of the gravity wave is eta. So eta is the wave height. So its time derivative has to couple to the normal component of the acoustic wave velocity. So that's one condition on the top surface. And the second condition is that the pressure is hydrostatically related to the wave height through rho g eta. So what you actually have is an ordinary difference. So you have a PDE in the volume coupled to an ODE on the top surface. There are some boundary conditions that allow the waves to propagate out without reflection. We actually solve in weak form, but that's a detail, another talk altogether. All right, so that's the forward problem, order 10 to the 14th degrees of freedom. Now, the inverse problem, as I said, given pressure recordings from sensors on the seafloor, infer the earthquake-induced seafloor motion, and then forward predict that to locations of interest on the coast. Right? So we wouldn't want to do a prediction everywhere on the coast, just for population centers, any kind of infrastructure, and do that under uncertainty. So what does it mean to do things under uncertainty? Well, we adopt the Bayesian framework or the statistical inverse problem framework. So the parameters, we're just going to give them a symbol here, m. So this is the time derivative of the normal seafloor motion. So that's m. And the data we'll just call d. And the data happen to be the pressures that we observe at some fixed number of locations, but over time. And there's something called the parameter-to-observable map, which says, all right, give me the parameters, and I'll tell you what you should read. Now, we want to invert that map. Okay, so we want to take the readings and figure out the parameters, but the forward map says, give me the parameters and solve the forward wave equation, and then extract the pressure values at the sensor locations. And that's the parameter-to-observable map. We want to invert it. The problem is it's ill-posed. It's not a one-to-one relationship. There are many different sets of parameters that would be consistent with the data because the data have noise. So the noise gives you some variability. So you have different models that can fit the data, but also because the data are very sparse. Sparse data, noise, that means the problem is ill-posed. And so we adopt the Bayesian framework, which puts a prior distribution on the parameter field, which encodes any kind of knowledge we have. How could this earthquake erupt? How could it emerge? And then the solution of the inverse problem is not a point estimate. It's not like, okay, here's the model that best fits the data. Here's a probability distribution that describes the probability that any particular model fits the data to within the noise. And that's really difficult because we're in 10 to the 10th parameter dimensions, and we're trying to characterize a probability distribution in 10 to the 10 dimensions. And then each point on that probability distribution is a 10 to the 14th degree of freedom wave propagation solution, because you have to compute the so-called likelihood. How are we going to do this? Okay, so the framework is Bayes' rule here, written because we're dealing in infinite dimensions, before we discretize, things are in infinite dimensions. So it looks a little bit different from the usual one. But if you move the prior over to the right-hand side, you have the posterior is proportional to the likelihood of the data given the parameters multiplied by the probability of the parameters, the prior probability, and that gives you the posterior probability of the model parameters given the data. Okay, now what we have going for us, and this makes the problem track, this is partially one of the things we exploit, is that the inverse problem is linear. So the mapping, if you apply boundary conditions into the problem, that's the boundary conditions enter linearly, so that's a seafloor motion. The coupled acoustic gravity equations are linear. The observation operator, that just picks up the pressure at different locations, that's a linear operator. So the entire chain is linear. And we're using a Gaussian noise model, very common, and a Gaussian prior, again, very common. So you put all that together, and then it turns out the posterior, which is this thing over here, is actually also a Gaussian. Its mean is what's called the map point, the maximum a posteriori point. I'll give an expression for that in a second. And its covariance matrix is given as follows. There's a covariance matrix. So F here is the parameter-to-observable map. Give me the parameters. I'll tell you what the data say. F star is what we call the adjoint, which at the discrete level is just the transpose. And then there's the prior that enters as well. And then you have to take the inverse of that. So that gives you the posterior covariance. That tells you about the uncertainty in the solution of the inverse problem. And then what's the mean of this distribution, the map point? Well, that's just this posterior that we just calculated here, multiplied by this vector, which is, give me the data, then I'm going to hit it with the transpose of the parameter-to-observable map. This is actually back propagation. So machine learning people call this back propagation. And then you hit it with the inverse of the Hessian, and that gives you the map point. So the idea is you'd pre-compute the posterior covariance. You're ready to go with this matrix. You have F star, you're ready to go with that. This is a vector that can be done offline. And so as soon as the data come in, you just take the data, propagate it through this product. That's it. Gives you the solution. No problem. Now, impossible. It would take you years to do this pre-computation. And the online part would take you years also. Why? Because this is a 10 to the 10 by 10 to the 10th matrix. And you can't even construct it. You can't even build this matrix because every column is defined by this parameter-observable map. So you'd have to solve the forward problem as many times as you have parameter dimension, and then you have to invert it. So that's out of the question. You can't do what I just said, you can't do. So what do people normally do? Well, they do a low-rank approximation of the data-informed part of this posterior covariance. This is a data-informed part. You do a low-rank approximation. Why can you get away with a low-rank approximation? Well, for many problems, you have significant ill-posedness. The eigenvalues of this operator decay rapidly. You can do a low-rank approximation. Then you use the Sherman-Morrison formula to construct an expression for the posterior, and then you go to town on it. I'm not going to talk about it because we can't do that here. We actually don't have low-rank structure. Yes, the problem is ill-posed, but the eigenvalues don't decay rapidly, and so we can't just represent this piece with a handful of parameters observed, a handful of wave propagations. Can't do that. If the problem had lots of dissipation, we could. If it was a so-called parabolic problem, those kinds of problems, yes, you can do this, or elliptic problems, but hyperbolic problems, no. Information is carried. This is the good news. This is what's going to let us invert and get good estimates of the solution, but it's also bad news from the algorithmic perspective. So what's good news for science is bad news for algorithms. All right, so what are we going to do instead? The first thing you might say is, well, do a surrogate, right? This is the AI, year, the year of AI, or the decade of AI, or just do some kind of machine learning surrogate, run a bunch of forward solves, create data, and then fit a representation. Sure, except, again, 10 to the 9th or 10 to the 10th parameter dimension. How are you going to populate 10 to the 10th dimensions? And you have to do a wave propagation solve at multiple points within that region. And you can't do that. Also, as I said, there's theoretical reasons to think that you're not going to be able to capture a low-dimensional subspace that accounts for the influence of the parameters on the data. So the mapping from the parameters to the data don't live in a low-dimensional subspace. Now, it's a linear subspace. Maybe there's a nonlinear representation, But how are you going to find that representation? How are you going to compute it? Again, 10 to the 10th dimensions. So this is out of the question. So we can't use surrogates. Okay, what are we going to do? Well, we recognize that the parameter-to-observable map, which again is defined by the solution of the wave equation, this is what's called an LTI system, linear time invariant, which belongs to a bigger class of autonomous dynamical systems. And in particular, what this means is the map from parameters m to data d, if you shift it by some time tau, it looks the same. If the earthquake happens today, if it happens tomorrow, if it happens in 100 years, the seafloor as it moves is going to affect the data, the pressure that you measure, in the same way. Now, is that exactly true? There could be tides, there could be changes. You know, the oceans are warming, so that can slightly change the density, and that might change the wave prop. But this is all the noise. These are all rounding errors. So, you know, for our purposes, it's a linear time invariant system. And what can you do with a linear time invariant system? Look, I'll give you the two-slide because this is the essence of what we do. So think of an abstract system that looks like the one at the top. So time derivative of a state variable is driven by linear dynamics on the right-hand side. Use the state, pressure, velocity, wave height, for example. And C is the operator that takes the source, the input, and maps it to the right-hand side of this dynamical system. So in our case, C is just an identity that lives on the seafloor because it takes the spatiotemporal seafloor motion and it maps it into the wave equation. Right? So this would be like an identity. There's boundary conditions that we're not worried about, some initial conditions. And then once you compute the state, you're going to hit it with an observation operator, which is going to give you the data. So our observation operator is very simple. Go measure the pressure. Go collect the pressure at some fixed points. Okay, so if you do a simple time-stepping scheme on this, you can do more complicated ones and get the same or similar result. But a simple time-stepping on this ODE, you can put together all the time steps, and here's what you get. You get that the data are related to the parameters. So the parameters at every time step, M0, M1, et cetera, related to the data at every time step, D1, D2, et cetera, through this block triangular system. It's lower block triangular because of causality. So lower block triangular. And if you carefully look at the different entries in this matrix, what you realize is every column looks like the column to the left, but shifted down one block. So this is a block Toeplitz matrix, and that's a reflection of the linear time invariance, the shift invariance in time. So the beauty of block Toeplitz matrices, first of all, there's a storage advantage, which you only have to store the first column because all the other columns look the same. So that helps a lot. And second, the block Toeplitz nature means that you can diagonalize a Toeplitz matrix with FFTs. So you don't have to do n squared work, you do n log n. And so that's fantastic. So that reduces the complexity quite a bit. And then finally, because of this block Toeplitz structure, if you go back and look at these, this one's a bit more subtle, but what you see is this wave propagation operator. Here you have a choice. You can operate to the right, and then you would have to solve the wave equation as many times as you have parameters, or you can operate to the left, which means that you have to solve the wave equation as many times as you have data. But because of this linear time invariance, that means that I don't need to solve for every datum. I don't have to have a source at every data point. So data means here not just the number of sensors, but also the instant in time when I measure. So that would mean hundreds of thousands of necessary adjoint solutions. So this is like back propagation. I only have to solve the adjoint wave equation for every sensor. If I have 100 sensors like that picture showed, which is the plan for Cascadia, I only have to solve the wave equation offline 100 times. Now, it might take hours on a supercomputer, but that we can do. That's just done once. All right, so putting all of that together gives us our algorithm. And so we can apply f and f star, the parameter-to-observable map, in a fraction of a second instead of order 1,000 seconds or so. So about a factor of 10,000 speed up. Here's some numbers. Once we do the offline part, when we go online, and we have to solve in real time. So we've stored just that one column, and we can write the full inverse solution, making use of FFTs and some dense linear algebra. First of all, it scales linearly in the parameter dimension and in the sensor dimension. as these expressions sort of indicate. So it's this nm is the parameter dimension, nd is the data dimension. And then if you do roofline analysis, so most of the kernels, unfortunately, we're not, we're memory bound. We're not to the right of the roofline chart. The algorithm is still memory bound, but the significant kernels are all running at the memory bandwidth limit. Now there's this thing down here, but these are forward and inverse FFTs that are of the data dimension, much, much smaller. So data dimension, again, is order 100,000, parameter dimension is order billion or 10 billion. And so they're down here. All right. So I'm not going to go through all the different phases, and I'm going to give you the bottom line, because we're running out of time. And so I'll give you a few scalings. Remember, there's an offline part where what we care about is scalability. There, we're solving the full wave equation. It's actually the adjoint wave equation. We're doing it once for every sensor. What we care about is scalability of the code. And of course, time to solution matters also, but we're trying to reach out to these really large systems. So this is on Dan's machine, Frontera. And if you go horizontally across, you see weak scaling. And if you go diagonally down along these lines, that's strong scaling. So, different instances. So let's take this one, for example. This is target size problem, about 10 billion parameters, close to 100 billion state degrees of freedom, velocity, pressure. So here on the full Frontera, going from 14,000 Frontera cores up to the full system, 459,000, it's very, very good. This is strong scaling diagonally, so that's really good strong scaling. And then if you look at the weak scaling on Frontera, going from one node, 56 Cascade Lake cores, out to the full 8,192 nodes that we have access to. That's weak scaling is 95% parallel efficiency. So it scales really well because we're using a high order method, so it's rich in arithmetic intensity, and it's wave propagation, so the right algorithm is explicit, and then everything is implemented in the right way. And it's all right. So this is really good scaling. We also have some scalings on Perlmutter. This is strong, and then this is weak on Perlmutter from one node, so 4 GPUs, 4 A100s, out to 4,000 A100s. And again, this is strong scaling, so you're at 0.94 parallel efficiency over that wide range. So as I said, we're working with a group at Livermore, and some preliminary runs have been done on El Capitan, on early stuff on Tsunamis, and it's looking really good, but there's more time. We've run on 3/4 of El Cap, so 32,000 GPUs, and the scaling looks super nice. All right, so I'm going to skip a few more issues about how we compute the uncertainty. And then I think I've given you the essence of the shift-invariance, but there's still some tricks you have to do, because I said this is a way where we can rapidly apply F and F star, the parameter-to-observable map and its adjoint. But you still need to invert, so that's F and F star. You still need the posterior covariance, and you still need to be able to hit this with the data vector. And there's some more details that are involved in that. So I'll just show you some results at the end here. Now, first we did a problem that had the scale of the kinds of problems that we're targeting. It's actually a bit smaller to just make sure everything is working right. So this was a box geometry with 128 kilometers squared by 4 kilometers in depth. So this problem is about 20 times smaller than the full Cascadia. Cascadia is about 1,000 kilometers long, about 250 kilometers wide. That's the computational domain. The 4 kilometers is about the right depth of the ocean. So the 50 seconds, so we're going to shake the ground for 50 seconds, collect data, and then see if we can invert and reconstruct that seafloor motion. The parameter dimension, so the total parameter dimension is on the order of 132 million, so not the 10 to the 9th or 10 to the 10th that we're targeting, but within an order of magnitude or two. The data dimension is 25,000. That's closer to the target of 100,000. So this would be 49 sensors multiplied by 500 measurement instance. The forward problem has about 1 billion spatial degrees of freedom instead of 50 or 100 billion. All right, this shows you that the problem does not admit a low rank representation. So there's no low dimensional subspace that captures the parameter-to-observable map, because the eigenvalues decay very slowly. Now, towards the end, they drop off quickly. Sure, you could get rid of this last bit here, but there's still information contained. I mean, this is only 2 orders of magnitude drop in the eigenvalues. These eigenvalues represent information gained from the data. So learning about the parameters from the data, you can quantify that in an information theoretic way from these eigenvalues. And this tells you that, hey, most of these eigenvalues, most of the directions in parameter space can be informed by the data. Luckily, these are waves that bounce up and down and they carry information with them. That's good from the scientific perspective and the public, the natural hazard perspective, but bad from the algorithmic perspectives. All right, so there's very little, that we can't learn from the data. So this is typically what we would do. Now, this is the box geometry, but we have sensors down here at the bottom in red. So this is where we place sensors. And then the blue points, the aqua points here on top, are the points where we want to predict wave motion. Okay, so these are the points where we're trying to predict inundation, not quite inundation, but at least the waves, because the acoustic wave propagation, the gravity wave, that approximation breaks down when you get into very shallow water. But you can get reasonably close, but then you have to, once you get to, say, 50 meters, then the assumption that the wave height is small relative to the depth of the water, that breaks down. So you have to stop just offshore. But once a 30-meter tsunami is heading towards your town, a kilometer offshore, I think that's a good enough prediction. All right. Here's what we do. In real time, we're computing this wave motion. So this is time on the horizontal axis, wave height on the vertical axis. And these are at different locations. So this would be point number 1, point number 2, point number 3. And different locations get very different wave heights and different dynamics. And then the shading is the Bayesian credibility interval. Okay, so this is 95% confidence interval. So we're giving the mean prediction and the interval. And then if you look closely, there's the exact solution in black dotted line, and then the prediction in red, let's say for this one. So the truth, the so-called truth, is a synthetic experiment, so we know what the truth is. So we're very close to it. Now, that's not always going to be the case. This is a model problem. We're putting sensors everywhere. We might not be able to afford to do that. And the prediction points are close to the sensors. It's a box geometry. So let's look at a real problem. Oh, but before I do that, let's just talk about the time. So there's the offline part, which was, this problem is a factor, 2 orders of magnitude smaller than our target problem. So about 6.5 hours. This was this is actually on Stampede 3 at TAC. 6.5 hours to do the offline wave propagations. There's some other minor stuff measured in the seconds and minutes. That's really nothing. And then in bold is the online part. So 57 milliseconds to compute the seafloor motion, to predict, this is the seafloor motion, 132 million parameters, inverse problem solved exactly, up to machine precision. There's no approximation here. There's no surrogate. There's no machine learned shortcut. Not much memory is required. The online part needs about 1 gigabyte of memory. The offline part, 50. Now, these are going to grow, again, by a factor of 20 to maybe 50 for the target problem. And then the quantities of interest, which are these wave heights at specific locations, those are calculated. I mean, you can't even measure it. Less than 1 millisecond and negligible storage. This 57 milliseconds of computing the mean seafloor motion, that was done on 8 nodes of Lone Star 6, which another one of Dan's machines, 24 A100s. We want to solve problems that are 20 to 50 times bigger. So in A100 terms, that's maybe 500 GPUs, but that can be afforded. And these are A100s. Then there'll be Blackwell is going to be much faster. So definitely real time, and on maybe 100 GPU Blackwell system that could be connected to this fiber optic cable. So this is all feasible. All right. So let's look at the Cascadia rupture zone. First of all, there is the mesh. So that's not a trivial problem. That took some work here. I'll just show you an animation of that. So the bathymetry is really complicated. You have the continental shelf out there, and then you have the continental slope, very complicated bathymetry, and then you get down to the ocean bottom here, down to let's say 4 kilometers depth. But over here, you're up at 100, 200 meters of water depth down to 100, and then it's up to. So our mesh actually, we've extended the mesh up to 30 meters of depth. What we've done is decompose the region into these blocks. These blocks are morally equivalent to hexahedra, and so we have a structured mesh within each block, and then we patch them together. So you could say it's a block structured mesh. And then, it follows the terrain, but that does mean some squeezing of elements and things like that. But in the past, we've done work on adaptive mesh refinement, and so this is the direction we're going to go. We're going to use octrees, octrees that are adapted to get into the small regions without penalizing the size elsewhere. Okay, so then let's look at so this is what a seafloor motion. So this is a plausible earthquake. So this is our collaborator, Elise Gabriel at UCSD said, okay, here's a plausible rupture on the Cascadia fault. This is what an earthquake could look like. What you're seeing on the left is the vertical displacement. So this is the thing that pushes the column of water up and creates the gravity wave. And on the right is just its time derivative. What we're inverting for is the thing on the right, actually. And so you can see that there is, this is seafloor. So there's uplift here, and there is subsidence on the coastal side. So, I mean, imagine what a terrible situation. I mean, you're on the coast, there's a big wave coming, and then you're sinking at the same time. So, but that's exactly that little cartoon that I showed in the beginning. That's what it tried to, that mechanism was explained in that cartoon. All right, so then the seismic waves, this is solid waves, are propagating on the seafloor. And you can see those seismic waves carry out. And what's left on the left is the permanent displacement. So there's a permanent subsidence on the continental side that makes up for the hundreds of years of uplift. So that suddenly drops down. It's going to be meters, 1 or 2 meters. And then on the ocean side, there's a net uplift. And on the right was the velocity of that. So that, if you just visualize the velocity, there won't be a permanent, the velocity waves propagate and they're done. But it's a very complicated wave pattern because of that very complicated bathymetry, right? Okay, so here is, so that's what's happening at the seafloor. What's happening at the surface, okay? So what's going on at the sea surface? So this is the eta, this is the gravity wave. On the left, the left is the pressure. So if you look at the left video, that's what the sensors are measuring. So it's backward in time. Let's go forward in time. So the sensors are measuring this pressure, acoustic pressure at the seafloor. And then on the right video is the gravity waves that have been produced on the surface by the uplift. Now, we don't actually go far enough in time. These are surface waves, but they're basically being dragged by the seismic waves on the seafloor. So it's not yet the big tsunami that takes some time, as the gravity waves move very slowly in the open ocean, and they move even slower, when they get to land, and then the amplitude builds up. But these are not yet the big tsunami, the waves that will create the big tsunami. This is only 7 minutes that we simulate up to. All right, but again, this is the kind of thing we want to predict. And then finally, the last thing I want to show is very preliminary inversions, as in like last night, because we only got the earthquake a week ago. So this is all very new. This is the truth on the left. This is uplift at how many? At 40 seconds. So we only did it for 40 seconds, not the full 7 minutes of shaking. This is the truth. This is what Alice sent us. So this is at 40 seconds. This is the uplift. This is I'm sorry, this is not the uplift. This is the sea surface height. This is the sea surface height anomaly. So this is the gravity. This is the uplift in the sea surface itself, and then we solve the inverse problem for the seafloor motion, like I said, and then we forward propagate it to the uplift. So this is what the inverse solution is. That's what the truth is. It's okay. It's missing details up here, but notice where the black dots are. So we had put pressure sensors down ahead of time, not knowing where the earthquake would be. And it turns out we have very little data in this region. There's a couple of sensors that are being lit up, but not that much. So what that means is we probably need a denser array. Also, if we go to longer time, this is 40 seconds. If we go to 400 seconds or 1,000 seconds, and we can't go to 20 minutes because by then no one cares. You can't make a prediction 20 minutes because the coast has been inundated. But more than 40 seconds. Let's say 5 minutes. 5 minutes. We're going to get more. All these sensors will then be lit up. They'll be measuring waves, and we can get a better inversion. All right. But already I was actually surprised at how good it was, given there are only a handful of sensors there. Okay. So the conclusions. But I've said all this stuff, and the main point is we can solve the inverse problem exactly in 57 milliseconds on 24 A100s for a problem that's still, admittedly, a factor of 20 smaller than the one we want to solve. The current work is to build data-driven priors, because the prior here is very simple, it's just smoothing. What we really want to do is run thousands of earthquakes that are plausible and build up a prior distribution from those 1,000 earthquakes. And then ultimately advise where the sensors should be placed. So it's an optimal experimental design problem that says, and this is the beauty of the Bayesian framework. Bayesian framework says, okay, this is the uncertainty in the parameters given the data. And so you can turn it around and you can say, well, where do I collect the data in order that the uncertainty is minimized? Okay, and that would inform design of this optical fiber system, and then solve other problems of interest. And the last thing, Nicholas asked us to have some, local connection. So there is, New Zealand is characterized by massive fault systems. There's a subduction zone over here. This is actually, it's from Wikipedia. It's incorrectly labeled. So the LLMs are learning this. Right? So this is not the Kermadec Trench. This is the Hikurangi subduction zone here. The trench is further up. So this is a subduction zone where the Pacific plate is subducting underneath the Australian plate. Then there's a North Island fault system, Wellington. There's a Marlborough fault system. There's the Alpine fault, which runs 600 kilometers through the spine of the South Island. And then it transitions over to another subduction zone. But in this case, Australia is subducting underneath the Pacific plate. So it's a very complicated fault system. Christchurch, can someone help me, is somewhere over here. That was actually not a fault at the boundaries of the plates. That was actually within a plate, intra-plate fault that had ruptured. And it was only, the 2011 event was magnitude 6.2, something like that. But it was right there, immediately there. And there probably had been some damage from the 2010 earthquake, which was a little bit to the west. And so buildings were already weakened by that other one. And that was a magnitude 7, a little bit east here. So there is a subduction zone. I've seen some simulations of tsunami waves that are propagated from this that can affect Wellington, that even wrap around and come in and affect Auckland, and even come around to the other side of the west side of the North Island. So there definitely is, and I know the GNS Science, which is an agency in New Zealand that does a lot of this work, and Jeff, I don't know, you guys do some of this stuff as well, that looks at tsunami hazards. Maybe we can contribute to the effort over here. All right. Thank you very much for your attention.
And that.